In this video, I'm going to briefly discuss various different algebraic structures, including groups, rings, and fields. This is a huge topic that covers a ton of information, and this is really just meant to be a brief overview. So first of all, what do I mean by an algebraic structure? Well, generally speaking, an algebraic structure is a collection of objects, and those objects could be numbers, but they don't have to be. They could be functions, matrices, they really can be anything. So we have these objects, and we also have one or more operations that we can perform on those objects. We could add them, or multiply them, or do something else. And we're going to categorize algebraic structures based on the properties of those operations, based on how many operations there are and what properties those operations have. Why do we care about doing this? Why do we want to categorize these algebraic structures? Well, there's a few reasons. One is that we can draw generalizations among number systems. So when we look out into the mathematical world and we see various different systems, including numbers and matrices and functions and all these other different things, using algebraic structures allows us to draw connections between those seemingly different systems. We can also, using this method, discover new systems that have similar properties to the ones that we're more familiar with. And finally, and this is probably the most important reason, is that we can prove theorems about all systems with the same basic properties. So one of the systems we're going to talk about is groups. So once we know what a group is, if we prove a theorem about all groups, then that theorem applies to all groups that ever have been and ever will be, including groups that we haven't even discovered yet. We'll know things about those groups because we proved theorems about all groups. So that really is the main reason why we care about algebraic structures. So speaking of groups, that's going to be the first type of algebraic structure we're going to talk about. So I'm talking about these algebraic structures kind of in order from least complicated to most complicated, although you can kind of argue that. It's really in the order of fewest properties to most properties. So the group is the simplest type of algebraic structure that we're going to talk about, simply because we've got these objects, the set of objects that we're calling G. So G here is the set of objects. And then we've got our operation, which I'm calling this sort of plus in a circle. And I'm just intentionally using an unfamiliar symbol there, just to indicate that this really could be any operation. It could be addition, but it could also be multiplication, it could be something else. So just some operation, we have to have a symbol for it, so I'm using this plus in a circle symbol. And then we've got three properties, and the three properties are associativity, and that means that if I have three of these objects, the way that I group those objects doesn't matter. So if I have three objects that I want to use this operation on, if I do the second one and the third one together and then tack on the first one, that's the same as if I do the first two together and then tack on the third one. The next property is identity. So that means that there's a special element that we'll call E, although again, that's just sort of a general term. So in practice, this element might be called 0, it might be called 1, so it's just some element of this group, so that when I use that operation with my identity element, nothing happens. So E plus G is the same as G plus E, and that just gives me G back. And then finally, the third property is inverse. So that means that for every element of this group, there's an inverse element, which we often write G to the minus 1. But again, depending on what this group actually is, we might have a notation for it that's different than that. But when we do our operation with G and its inverse, in either order, we just get back the identity again. Okay, so this is all very abstract. Let's talk about some examples. Okay, so there's lots of examples of groups. So let's start with probably the simplest example, which is the set of integers. Now I'm using notation here. This bold-faced Z just represents the set of all integers. So that's whole numbers, positive, negative, and 0. And the operation we're using is just regular old addition. And so to verify that this is a group, there's three things that we need to check. We need to check that addition is associative, which means we need to know that for any integers a, b, and c, a plus b plus c should be the same as a plus b plus c, and that's a property that we know about integers. We also need to make sure that there's an identity. In this case, the identity for integers is 0, because a plus 0 is equal to 0 plus a, which is equal to a. Notice that I'm not calling it E like I did on the previous slide, because in this case we know what that identity is. We know that identity is a good old 0. Finally, we have a requirement that we have to have an inverse for every integer. And in this case, for every integer a, the inverse of a is actually negative a, because negative a plus a gives us back that identity, which is 0. So again, I'm not calling it a to the minus 1, because in this case, we specifically know that if I have any integer a, the additive inverse of that integer a is negative a. So those 3 lines there tell me that this is group. So I'm not going to go through and check all the properties for all of these examples, but that's the idea. That's what you would have to do to verify that these things really are groups. So just going down the line here, the next example is a set of integers mod n. So again, if you're familiar with modular arithmetic, which you should be if you're watching this video, the set of all integers mod n with addition of congruence classes makes this a group. The set q, the set of rational numbers, that's fractions where the top and the bottom of the fraction are integers, and the bottom, of course, isn't 0. And I can add those rational numbers. That gives me a group as well. The set r star, the set of non-zero real numbers with multiplication, is also a group. And again, the identity in this case, since the operation is multiplication, the identity would be the number 1. Now, notice here that this is not meant to be an exhaustive list. Certainly there are more things on this list. The set of non-zero rational numbers with multiplication is also a group. The set of real numbers with addition is also a group. So there's lots and lots and lots of examples. Another different kind of example is the set of invertible functions with function composition. So if I compose functions, that operation is associative. So f composed with g composed with h is the same as f composed with g composed with h. So we've got associativity. Because I'm insisting that the functions are invertible, each function is going to have an inverse, and then the identity element is actually the identity function, which we might call I, and this function just has the boring formula that I of x equals x for all x. Another different kind of example is a set of 2 by 2 invertible matrices with matrix multiplication. So again, I'm insisting on the matrices being invertible so that I get that inverse requirement for being a group. The identity element is going to be the identity matrix, and then we know that matrix multiplication is not necessarily always commutative. A times b is not always equal to b times a, but it is associative, because if I have 3 matrices, a, b, and c, a times b times c like that is the same as a times b times c like that. But a times b is not always equal to b times a. So not always, anyway. So when a group has that additional property, when a times b always equals b times a, we say that it's a commutative group, or sometimes an abelian group. But a group does not require that commutativity. So you're still allowed to be a group even if a times b does not always equal b times a. So some of these examples are abelian groups, are commutative groups, but some of them are not. So our next example of an algebraic structure is a ring. So this is a little bit more complicated than a group. In this case, we have 2 operations, which I'm calling sort of the same plus in a circle thing, and then star. And so we think of those as being addition and multiplication. So again, I've chosen symbols that are reminiscent of those symbols that we're used to, but not necessarily the exact symbols that we normally use. So what do we have to be a ring? Well, again, using some of the terminology that we've already developed, one of the requirements is that R has to be a commutative ring under that addition property. So in this case, that means there's an additive identity, there are additive inverses, addition is both associative and commutative. So all of those things have to be true. Now getting to the star operation, multiplication, has to be associative. There has to be a multiplicative identity, so there's and since it's a multiplicative identity, we usually call it 1, even though it might not actually be the real number 1 that we're used to. So that's a little bit of a notational thing. And then finally, the multiplication and addition operations interact with each other in the way that we would expect. In other words, we have distributivity, which we have left distributivity here and right distributivity there, because the star operation, the multiplication, does not have to actually be commutative. Again, a times b does not always have to equal b times a. Now, something to note here, you may have seen this property here, this multiplicative identity missing. It really is standard for a ring to be required to have a multiplicative identity. But sometimes you'll see that we might care about a situation where we have all of the rest of these properties, but we just don't happen to have a multiplicative identity. Some people give this type of structure where we have everything for a ring except a multiplicative identity. Some people will call these RNG, where we write the word ring but we leave out the I. I've also seen this called a wrong, RONG, because it's wrong for a ring to not have a one element. So there are reasons why we might study something that has all of the properties of a ring without the multiplicative identity. But it really is standard to require the multiplicative identity to be there for this to be considered a ring. So if we leave this property out, then we have, again, a ring with no I, or a wrong with an O instead of an I. That's if you have everything except multiplicative identity. So again, there's lots of examples of rings. So again, to be a ring, you have to have an addition and a multiplication, and those addition and multiplication have to have lots of different properties. So to actually verify that something is a ring would be quite involved. You'd have to demonstrate a lot of different properties. I'm not going to go through those details here, but just to give you an idea, that would be a lot of work. So the set of integers with addition and multiplication is a ring. The set of integers mod n is also a ring. The set of all 2 by 2 matrices, so the matrices don't have to be invertible, because to be a ring you don't have to have multiplicative inverses. You do have to have additive inverses, but the additive inverse of a matrix is just what you get by putting minus signs in front of every entry of the matrix. So that turns out to be a ring. Another good example of a ring is a set of polynomials. So this r brackets x here, that's notation for the set of all polynomials with real coefficients. And again, we can add and multiply polynomials. And as I've said before, there's lots and lots and lots and lots of examples of these. These are just a few. Again, we're just trying to get an overview here, trying to scratch the surface of these different kinds of algebraic structures. Next up in our discussion of algebraic structures, a little bit more complicated, is something called a field. So a field is very similar to a ring. We've got 2 operations, addition and multiplication. So, and now that we've established some of this terminology, we can describe a field by saying that this field is a commutative ring under addition and multiplication. So now when I say commutative ring, I'm talking about the multiplication being commutative. A ring, to be a ring, the multiplication does not have to be commutative, but to be a field, the multiplication does have to be commutative. And then finally, the property to be a field is that we have to have multiplicative inverses for every element of this field other than 0. So for every f not 0, there's some other element g, so that f times g is the same as g times f, because the multiplication is commutative, and that gives me 1, the multiplicative identity. So a field you can think of as a ring where the multiplication is commutative and every element has a multiplicative inverse other than 0. As usual, lots of examples of fields, some of which are familiar to us. Integers mod p, where p is prime, is an example of a field. If you're looking at integers mod n and n is not prime, then not every element of that ring will have a multiplicative inverse. But when p is prime, then everything other than 0 will have a multiplicative inverse. Again, other common examples are q, the set of rational numbers. Remember, that's fractions, where the top and the bottom are whole numbers. R, the set of real numbers. C, we haven't seen this yet in this video, but C is the set of complex numbers. That's things that look like a plus bi, where I is the square root of minus 1. So I'm going to spend a little bit of time talking about this last example here, which is q brackets the square root of 2. So this is everything that looks like a times the square root of 2 plus b, where a and b are rational numbers. So I just want to sort of demonstrate how these operations would work. The operations here are just addition and multiplication of numbers. So if I had 2 of these guys that I wanted to, let's say, add together, so 3 times the square root of 2 plus 4, and let's say I wanted to add that to 4 times the square root of 2 plus 6, I would just collect like terms. So 3 radical 2 plus 4 radical 2 would be 7 radical 2, and then 4 plus 6 is just 10. So you just add them like that. If I wanted to multiply, let's say I had 2 radical 2 minus 4, and then negative 5 radical 2 plus 3, and I wanted to multiply those together, I would just use FOIL and multiply this out like I normally would. So 2 radical 2 times negative 5 radical 2 is my first. So if I'm thinking FOIL, first, outer, inner, last. So there's my first. My outer is 2 radical 2 times 3. My inner is negative 4 times negative 5 radical 2. And my last is just negative 4 times 3. Now I'm going to simplify these. 2 radical 2 times negative 5 radical 2 is going to be negative 20. 2 radical 2 times 3 is going to be 6 radical 2. Negative 4 times negative 5 radical 2 is plus 20 radical 2. And then negative 4 times 3 is negative 12. And then again, I just collect like terms. So 6 radical 2 plus 20 radical 2, that's 26 radical 2. And then negative 20 minus 12 is minus 32. So that's how this field works, right? So that's how you add, that's how you multiply. Now, it takes a little bit of thought, though, to think, why is this a field? So you can maybe see all of the properties pretty clearly, except why do we have multiplicative inverses? Why would there have to be an example that shows us why this has a multiplicative inverse? And the way that we see why there are multiplicative inverses in q brackets the square root of 2 is actually kind of clever. So what we're looking for is if I had, let's say, 3 radical 2 plus 4, and I wanted to say, okay, what do I multiply that by? Some other a radical 2 plus b, and what I want to get back is 1, right? What I want to get back is the multiplicative identity. So what we really want to go here, and so this is my sort of thought process, what I really want to go here is 1 over 3 radical 2 plus 4. The only problem is that 1 over 3 radical 2 plus 4 is not of the form a radical 2 plus b. But I can do something kind of clever to get it into that form. What I'm going to do is multiply that fraction, top and bottom, by 3 radical 2 minus 4. This is sometimes called rationalizing the denominator, something you might have done back in high school. But when we do this, what we get is, on the top, we get 3 radical 2 minus 4. And on the bottom, because that's a difference of 2 squares, we get 3 radical 2 squared minus 4 squared. And that's going to be an integer. So we get 3 radical 2 minus 4. On the bottom, 3 radical 2 squared is just 18. And 4 squared is 16. So that's just 3 radical 2 minus 4 divided by 2. And I can write this in the form a radical 2 plus b. They're writing that as 3 halves radical 2 minus 2. And remember, 3 halves is allowed because I'm in Q, I'm in rational numbers, so that's okay. And there wasn't anything special about the numbers 3 and 4 here. I could have done this with any element of q brackets the square root of 2. So that's really the explanation for why q brackets the square root of 2 here is a field. Because everything else is pretty clear, I think, except for maybe the multiplicative inverses. But this isn't a proof, what I've written here, but this gives you the idea of what the proof might look like, of how I would justify why everything has a multiplicative inverse. Okay, I want to talk about one more type of algebraic structure that you might be needing to know about, and that's vector spaces. So vector spaces are by far the most complicated in terms of the structure of how many things are going on, because not only do we really have two sets. We've got a set of vectors, v, and then we've also got a set of scalars, which we call f. And we call it f because f is going to be required to be a field. So v is a commutative group under addition. So we've got one of our operations is vector addition. We take two things in v and add them together, and that's going to be a commutative group. So we're going to have an identity element, the 0 vector. We have inverses, additive inverses, and we have associativity of addition and also commutativity. F by itself is a field under multiplication. So that's taking two scalars and multiplying them by each other. So we're going to have an identity scalar, which is going to be the number 1, or we're going to think of it as the number 1 if the field isn't numbers themselves. And then we've got an operation that lets us combine scalars and vectors, and this is scalar multiplication. So if I've got some scalar s and some vector v, I'm going to always have to be able to multiply that scalar by that vector. And then we've got some additional properties that talk about how these things interact. So if I take the scalar 1 and multiply it by v, I just get v back. If I take two scalars, a times b times v, should always be equal to A times B times V. And then we've got distributivity of scalar multiplication over vector addition, and also of scalar multiplication across scalar addition. So it's a whole bunch of properties that when we put them all together, we get this thing called a vector space. So we've got lots of examples of vector spaces. Probably, if you've ever seen vector spaces before, the one that you're most familiar with is this thing Rn, which is the set of n tuples. Sometimes we can think of these as column vectors. You might be more familiar with them in this form. So a1 through an. So it's just a list of numbers, in this case real numbers, and that's going to be a vector space over the set of reals. I can add two vectors, and that's a commutative group under that operation. The scalars themselves, R is a field under the normal real number operations, and then we can also multiply any vector by a scalar. Another example that might be a little bit less familiar is the set of functions from the real numbers to the real numbers. Think calculus functions here. So a function that when I plug in a real number, I get back a real number. And that's going to be a vector space over the set of real numbers. Again, just briefly, I can add two functions. I can multiply a function by a scalar and get another function. So that gives me a vector space. The set of complex numbers can be thought of as a real vector space. Now, I'm skipping some of the operations, right? So this set C, if I think of it as a vector space, I'm ignoring some of the operations that can be done on complex numbers. So when we think of a vector space, we think of adding two vectors together. We think of multiplying a vector by a scalar. But if my vectors are complex numbers, it's actually possible to multiply two complex numbers, and that operation also has a bunch of cool properties. But if I'm thinking of it as a vector space, I'm ignoring that operation that I can do of multiplying two vectors together. So in a vector space, if you have the ability to multiply two vectors together, you just ignore that. You pay no attention to that. Another example that's kind of like the complex numbers is this thing q square root of 2 that we were talking about. Again, I have the ability to multiply two of those vectors together, but when we think of it as a vector space, we completely ignore that. And again, there's many, many, many examples of vector spaces. Talking about vector spaces and their properties and the things that we can do with vector spaces leads to a discussion of basis and dimension and all sorts of other things that you might talk about in a linear algebra class. And again, that's not the focus of this video, but it's certainly something that we could talk about in another video. And this really is the essence of what algebra is. So when you tell somebody you're studying algebra, and what you really mean is that you're studying abstract algebra, it's easy for a layperson to get confused. Most people think of algebra as 2x plus 5 equals 0, solve for x. But that's not what algebra, modern algebra, abstract algebra, that's not what that really represents. That represents this sort of really high-minded, let's try to find common features of all of these different numerical and algebraic systems that we think about. Polynomials, matrices, numbers, all of these different things. What are some common features that we can find? That's what algebra is all about.